Okay, this is Module 1, Part 2, Units of Measurement. So, properties of matter are quantitative, and the units for scientific measurements are those of the metric system. So the units in chemistry are the SI units. So really there's 7 base units from which all other units can be derived, right? And so that's really key. So really the most important are, these top 5, okay? Everything above this line is extremely important. You need to know that the SI base unit for mass is a kilogram, length is a meter, time is a second, temperature is Kelvin, the amount of substance is a mole. Okay, and you should know those abbreviations. So a measured quantity has to have both a number and a unit. So always remember to include a unit, because if I say it took me 5 to get here, what does that mean? Minutes, meters, seconds? So you make sure to say the units along with it. And so the majority of all measurements that use the SI units will also use some sort of prefix to indicate either a fraction or a multiple. Okay, and some of the most common are listed here in Table 1.5. And honestly, the closer you are to the middle, probably the more commonly they're used, and the more important to know. So something like a kilo is a kilogram, abbreviated K, means that there's 10 to the third of whatever is there. So here we have 1 kilowatt, means that we actually have 1 times 10 to the third watts, okay, or 1,000 watts. So you need to memorize these prefixes, and you need to understand exponential notation and how to go back and forth using it. If you need a review for that, you should probably see Appendix A1 in the textbook. Alright, so we're going to look at the different major categories and talk about their SI base units as well. The first we can talk about is mass. Okay, and so the SI base unit of mass is the kilogram, and mass is just a measurement that reflects the amount of material in an object, right? So a lot of times we get confused when we talk about mass and weight. Okay, oftentimes we think they're the same, but that's not true. The weight of an object actually has to do with the force that's exerted on it by gravity, right? Where if you're in space, there is no gravitational force, very limited, it's very weak, so an astronaut can be weightless, but it doesn't mean that they're massless. Okay, and so that's what this figure on the bottom right kind of shows, that weight can change from place to place, but mass is constant. Okay, so you should remember that. So we can also talk about temperature. So what is temperature? Well, temperature is a physical property, right? It's the measure of the average kinetic energy of the particles in a sample. It's how hot or how cold something is. Okay, and heat always flows spontaneously from an object at high temperature to one at low temperature. Right? So if you take your hand, you stick it on the stove, what happens? The heat flows from the hot object to the cold object, and you burn yourself. So when we talk about temperature, most common circumstances, we're always talking about Celsius or Fahrenheit. But for scientists and for people talking about the SI unit for temperature is Kelvin, abbreviated K. It's not degrees Kelvin, it's just Kelvin. All right? So, like I said, in scientific measurements, most of the time you're going to encounter Celsius or Kelvin. Okay? The Celsius scale is based on the properties of water, so 0 degrees is the freezing point of water, 100 degrees is the boiling point of water, and so we can see that on this middle thermometer. Okay, we have Kelvin, which is shown over here on the left, and we have Fahrenheit shown here on the right. And so you can kind of see how those compare. All right, probably the most important equation you need to know right now is that Kelvin is equal to degrees Celsius plus 273.15. Okay, so if you have degrees Celsius, sorry about that. If you have degrees Celsius and you need to convert to Kelvin, you just plug in your degrees Celsius plus 273.15 and you get the amount of Kelvin. Okay. In most cases, if you just remember 273, I'm okay with that. And then you need to be able to convert from Fahrenheit to Celsius or Celsius to Fahrenheit. And I would give you these equations down here, but you should know these as well. Okay. So now moving on, we can talk about how these different 7 SI base units can really be used to obtain derived units. Okay, examples of these derived units are listed in this table, just a couple of them. So when we talk about speed, we're talking about distance versus time, distance over time, right? So when we talk about length, we're talking about meters. The SI base unit for length is meters, and when we're talking about time, it's seconds, so meters per second. Same thing for like volume. Volume is equal to length cubed, so we measure that in meters cubed. whereas density is the amount of mass per volume, so our units for that is grams per centimeter cubed or grams per milliliter. So that kind of leads us into expressing volume in these SI units. Okay, so for volume, which is the derived quantity, basically that means that we have a symbol of meters cubed. And so most commonly we refer to volume as liters or milliliters. Okay, and so we can really think about a liter being a cube that's 1 decimeter long on each side. Okay, so that's shown here. Okay. We can also have a milliliter, which is a cube that is 1 centimeter long on each side. Okay, so that's shown here. All right, and so when we talk about volume, volume is equal to length cubed, so the SI units are meters cubed. Right, so 1 centimeter cubed is basically equal to 1 milliliter. So this is equal to 1 milliliter, right, which is shown here. And you can see that there's basically 1,000 of these little centimeter cube blocks in 1 decimeter cubed, which is equal to 1 liter. And so 1 milliliter is equal to, or 1,000 milliliters is equal to 1 liter. Okay, same thing, there's 1,000 centimeters cubed in 1 decimeter cubed. Alright, so when we measure volume in the laboratory, this can be accomplished by a number of methods and different glassware. And that really depends on the precision and the accuracy required. The syringe, the burette, and the pipette, okay, are all more precise than graduated cylinder. But a volumetric flask will help you deliver a specific volume of liquid, so it's very precise. Alright, next we can turn to density, another derived quantity. So density is the amount of mass in a unit volume of substance. It's a physical property of substance. And the units are grams per milliliter. So when we report density, temperature should always be specified. If it's not reported, you should assume that it's room temperature. Okay. One of the very important concepts about density is that when you combine two different liquids, okay, that don't mix, basically the less dense liquid will float on top of the more dense liquid. So density is extremely important. You should know the formula, which is equal to mass over volume, right? If you remember those units, it's grams per milliliter or grams per centimeter. And so basically you can, grams per centimeter cubed, so you know that you're measuring mass divided by volume. Okay. The density of water is going to be 1 gram per milliliter or 1 gram per centimeter cubed. You should know that one. All the others I'll either give to you or you'll be able to calculate. Alright, so now we can really turn to looking at, when we do these different measurements and we take different measurements, what kind of numbers can we expect? Okay, because there's uncertainty in measurements. And there's really two kinds of numbers. There's exact and there's inexact. So when we talk about exact numbers, we're talking about like that there's 12 eggs in a dozen, that 1,000 grams is equal to 1 kilogram. These are exact numbers. Inexact numbers really refer to different measurements. Okay, because inexact numbers have some uncertainty, and numbers from measurements are always inexact and have some level of uncertainty due to both equipment error and human error, as well as there's always uncertainties which exist in a measured quantity. So another important concept is that different measuring devices have different uses and different degrees of accuracy. And so we can see that here with the graduated cylinder, the syringe, and the burette. These are going to deliver variable volumes. Okay, they're close, but they're kind of variable. A pipette will deliver a specific volume, and a volumetric flask actually will contain a specific volume because there's a little line here on the volumetric flask that you fill up to, and that is the exact volume of this volumetric flask. So if this was a 100 milliliter volumetric flask, that line equals 100 milliliters. Okay? Alright, so now we can turn to precision and accuracy. Precision and accuracy are frequently discussed with measurements. It's important to understand the difference between the two. Alright, an easy way to think about it is about playing darts, and so that's what's shown over here on the right. Okay. So accuracy refers to the proximity of a measurement to the true value of a quantity. If you're playing darts, all the darts are accurate and they hit the bullseye, right? So here you're hitting the bullseye. They're all accurate. Whereas precision refers to the proximity of several measurements to each other. So thus in darts, it means they all hit the same spot. Okay, could or could not be the bullseye. And so in this top figure, you can basically see that you're accurate and precise because all the darts are grouped together and they're all in the bullseye. You could have poor accuracy but good precision, where basically none of them hit the target, the bullseye, but they're all grouped together, so they have good precision. Or you could have poor accuracy and poor precision, where basically the darts are scattered all over the board and none of them are hitting that target. So precision is what we describe as standard deviation. That is the difference between individual measurements and the average. So a low standard deviation means that the values are grouped very closely together. But you have to remember that a precise measurement can still be inaccurate. Okay? So imagine if you weighed yourself on an uncalibrated scale. Right? You may weigh yourself and it continues to tell you that you're 20 pounds less than you thought. You get off, you weigh again. You get off, you weigh again. Well, every time you're still 20 pounds less than you thought. So no matter how many times you weigh yourself, you get the same value, but it's still an inaccurate value. Okay? So the scale is precise, but it's not accurate. Alright, so now we can turn to what's termed significant figures, which just refers to the digits that were measured. Okay? And so if we determine the mass of an object on a scale, right? Here's our scale, right? And so this scale reads to 0.0001 grams. That's how accurate it is. Okay? So if we measure an object, right, and we find that it is 5.6781 grams, okay, we would say that it's plus or minus 0.0001 grams, because that's how accurate this scale is. Okay. Well, in science, we basically drop this plus minus, right? We don't actually use that because we understand that there's always some uncertainty in the last digit reported for any measured quantity. Okay. And so if we look at this thermometer in this picture, right, we can basically see that there's marks at both 25 degrees and 30 degrees on there. Right? But we actually estimate that the last digit is about 27 degrees Celsius. So we estimate that it's a 7 instead of a 5 or a 0. So we are actually uncertain of that last digit. And so all digits of a measured quantity, including the uncertain one, are called significant figures. So we can determine the number of significant figures, but this is always a difficult concept for most students. So what I try to do is try to give you a specific set of rules that you can memorize, and practice these rules, and you'll start to understand significant figures, because you're going to use these in lab as well as in most chemistry classes. So basically there's 5 rules. The first is that all non-zero digits are significant. So basically anything that's 1, 2, 3, 4, 5, 6, 7, 8, or 9 are all significant. Although zeros between two significant figures are themselves significant. So here we have 105 grams. So we have a 1, we have 5, right? And there's a 0 in between. It is significant because it is basically held captive by two significant figures. The third rule is zeros at the beginning of a number are never significant. So here we have 0.05. There is only one significant figure. Or if you have something like 0.003 centimeters, you still only have one significant figure, okay, which is this 3. None of the zeros at the beginning of a number are significant. However, zeros at the end of a number are significant, okay, if there's a decimal point. Okay, so here we have 0.0500 centimeters. Okay, the zeros at the beginning are not significant, so we can basically cross those out. The zeros at the end of the number, because there's a decimal, are significant, and so for this 0.0500 centimeters, we have 3 significant figures. The next one is 3.0 grams. We have a decimal. That 0 at the end is significant, and so we have 2 significant figures. If I just give you anything like that that has a decimal, then you should remember that those zeros are significant as long as they come at the end of the number. Lastly, zeros after the number, but before the decimal point, are ambiguous. Okay, and so really we need exponential notation to clarify. And so you need to be able to convert from 10,300 grams into exponential notation, or taking something like 1.03 times 10 to the 4th, converting that and knowing that's 10,300 grams. Okay, and so for significant figures, 1.03, the 0 is held captive. There's 3 significant figures there. The next one is 1.030. That one's going to have 4 significant figures because the 0 at the end is significant because there's a decimal, as well as the 0 held captive. Same thing in this last one, 1.0300 times 10 to the 5th. Basically here we know that all three zeros are significant because of the decimal, and this 1 0 is held captive, right? So memorize those rules, make sure to practice that. Two other important rules are when you have different calculations from different measurements, you still have to figure out how many significant figures there are. Okay. So when calculations are involved, you need to remember the least certain measurement limits the certainty of the calculated quantity and determines the number of significant figures that are available in the final answer. Okay, the final answer always wants to be reported in just one uncertain digit. So the first rule is when we look at addition or subtraction. Answers are rounded to the least significant decimal place. So really all that says is that if we took 14.3505 grams, right, and we added that to 2.65 grams, we just look for the least number of significant figures past the decimal place. So in this top one, we basically have 4 significant figures after the decimal. In 2.65, we just have 2 significant figures after the decimal. And so our final answer is reported in 2 significant figures past the decimal. Okay, so it doesn't matter what's before, it's just what's after that decimal. For multiplication and division, it's slightly different because answers are rounded to the number of digits that correspond to the least number of significant figures in any of the numbers used in the calculation. So in this example, this is an error. This should be 10 to the 4th, and this should be 10 to the 3rd. Okay, so basically here, since we have scientific notation, all we have to do is look at this beginning number, which has 3 significant figures, 3, 2, and 9. We're multiplying that times 0.2501, right? Well, we know that all zeros before the number are insignificant, so it's not a significant figure. Whereas 2, 5, 0, and 1, the 0 is held captive by the 5 and the 1, so there we have 4 significant figures. Okay. So here we have 3 significant figures, here we have 4, so our final answer is in the least number of significant figures, right? So basically we have 3 significant figures in our final answer. Same thing for division, you just figure out how many total number of significant figures there are and report your answer in that number. The last thing is rules for rounding off. Basically, if the leftmost digit is less than 5, you leave it unchanged. If it's greater than or equal to 5, then the preceding number is increased by 1. Okay, that's just general. Alright, so the last topic of this video is dimensional analysis, and it's one of the most important concepts in this class. Dimensional analysis is just a conversion from one unit to another using a known conversion factor. A conversion factor is an exact number, so we don't actually need to worry about significant figures, which can also be called sig figs. So an example of a conversion factor is that in 1 inch there's 2.54 centimeters, right? And so we can write the conversion factor either way. We can either write that 1 inch over 2.54 centimeters or that 2.54 centimeters over 1 inch. Okay? So basically it doesn't matter which way we write it, and we'll see why we write it one way instead of the other. So when you attempt these different dimensional analysis type problems, there's a few questions that you need to ask. Okay? What units are given, what units are desired, and what conversion factor or factors are needed. So if I told you take 2 inches and convert 2 inches to centimeters. So we have 2 inches and we want to know how many centimeters that is. Okay? Well, if we answer these questions, first, what units are given? Well, we know we are giving inches. What units are desired? Well, we want centimeters. Alright? So what conversion factor then is needed? Right? Well, we know that 1 inch is equal to 2.54 centimeters. So we can use that conversion in order to calculate from 2 inches to... Well, when we do this, we basically can set it up using this equation, or this formula. We have our given unit, okay, and we want our given unit to cancel out its units to only leave our desired unit. And so if we write our given unit first, and we put our given unit in the denominator of the conversion factor, and put our desired unit as the numerator, the given units then cancel out, leaving only the desired unit at the end. So, if we take our 2 inches, right, and we use our conversion factor that there's 1 inch and 2.54 centimeters, and we multiply this, right, well, if we put inches in the bottom and we put centimeters up top, our inches can cancel out. And so then we end up with 2 times 2.54, so we get 5.08 centimeters is equal to 2 inches. And so that's how you want to approach these different problems. The last note is that dimensional analysis of volume is a bit tricky. So volume is measured in units cubed. So anytime you're talking about cubed units, the value and the units must be cubed as well. So for this example, what is the mass in grams of 2 cubic inches, so 2 inches cubed, of gold? And you have the density of gold, which is 19.3 grams per centimeters cubed. Well, if we answer our first 3 questions, first, what is our given units? Well, we're given cubic inches, right? What is our desired units? Well, our desired units is what is the mass in grams, right? And so the conversion factors that we need are, one is we need the density, which tells us, helps us relate mass and volume, okay? But then we're going from inches to centimeters cubed, and so we're going to need a conversion of inches to centimeters, okay? What I say is confusing here is that we know that 1 inch is equal to 2.54 centimeters, right? But here we're talking about cubic inches. It's not the same as inches. And so to get cubic inches, we have to cube this whole thing. Which means that if we're doing the conversion, we also have to cube the number of centimeters. So that's cubed. And so both the value, 2.54 centimeters, okay, is cubed, as well as centimeters is cubed. And so that's how we get to here, where you have 2.54 centimeters cubed is equal to 1 inch cubed. And so you basically take 2.54, cube it, which is 16.39. Centimeters is cubed, so we have centimeters cubed. And now we can use this conversion factor in order to calculate the number of, or the mass in grams of 2 inches of gold. So, if we're looking for the mass in grams, okay, and we're starting with 2.00 inches cubed, right? Well, if we use our conversion factors that we had from the last thing, we know that in 1 inch cubed, there is 16.54 centimeters cubed, right? So here our inches cubed will cancel out because our desired units are centimeters cubed, our given units are inches cubed. We want the inches cubed in the denominator. Well, now we're trying to get to grams, right? And we need to convert centimeters cubed, which we're left with, to grams. And so we can use our other conversion factor, which was the density for gold, which tells us that in 1 centimeter cubed, there is 19.54 grams. And that's just the density. And so now we can solve. And so we can cancel out units that cancel from the numerator to denominator. Inches cubed, centimeters cubed, centimeters cubed. And so now we're just left with grams. And if we basically calculate everything in the numerator divided by everything in the denominator, we get 633 grams.